Hello class, Professor Anderson here. Let's ask the following question. What is your acceleration right now? And to be specific, let's talk about the acceleration that we are experiencing as we are on this spinning Earth. Forget the fact that the Earth is spinning around the sun as well. Let's just worry about due to the spinning Earth. All right, what we said was centripetal acceleration is v squared over r. So we need to know how fast we are moving, and we need to know how big that circle is that we're moving on. So we're going to need your help here. How do we figure out v? Well, let's think about it for a second. If this is our particle v moving in a circle, and it moves on a radius r, what is v equal to? V is just how far you go, once around would be a circumference of 2 pi r, divided by how long it takes, the period of one revolution. Right? So let's plug that in here. We've got 2 pi r over t, quantity squared. We're going to divide by r. And now look what happens. We've got a 4, we have a pi squared, we have an r squared, we have an r in the bottom. That capital T slips into the bottom with a squared on it. We can cancel one of the r's, and we get 4 pi squared times r divided by t squared. Okay, so on the Earth, what do we know? Well, we know t, right? What's t? What is the period of one revolution of the Earth on its own axis? Yeah, in the blue? 24 hours. 24 hours, that is of course not SI units, and so we got to multiply it by 3,600 seconds per hour. So somebody try that in your calculator and tell me what you get. What about R? Anybody know what R is for the Earth? That's a little more tricky. Okay, why don't you take 2 seconds, look up what R is for the Earth, and let's come to a consensus on that. Anybody get a number for this one yet? Yeah, what'd you get?
86,400.
86,400?
Correct.
86,400 seconds. Okay. And then did we find the radius of the Earth? Yeah, what'd you get for the radius of the Earth?
6,378.1 kilometers.
6,378.1
Yeah.
kilometers. That's pretty exact. Okay. So we need to put this in SI units, which is of course meters, and so we get 6.3781 times 10 to the 6 meters. Let's put all those numbers into this equation now and see what we get for the acceleration. Okay, we took our numbers and we plugged them in over here. Did anybody get an answer for that? while you work it out, I'm going to approximate it. So let's approximate this as the following. 4 pi squared, pi is 3, squaring that, I get 10, so that's about 40. I'm going to multiply that by 6.4 times 10 to the 6, and then we're going to divide by 8.6 times 10 to the 1, 2, 3, 4. And so that'll get us, what? 40 times 6.4 is 240, 250. We're going to divide by 8.6. And then we've got a 10, oh, we forgot to square it, right? That thing is squared, so we've got a squared there, and that gets us a 10 to the minus 2. 8.6 squared, that's pretty close to 9 squared, which is 80, a little less, 70. 70 goes into 250, maybe 4 times, 3.5. So let's say 3.5 times 10 to the minus 2. We're probably off. Anybody get a real answer? Remember to square that guy right there. Yeah, what'd you get?
0.03373.
3373. Like that?
Mm-hmm.
Okay, so our guess was pretty good. 3.3 times 10 to the minus 2, and the units on this are, of course, meters per second squared. So that's how fast you are accelerating right now. Is that a big acceleration or is that a small acceleration? Well, let's compare it to something we know. What we know is gravity is 9.8. So this is 0.03 compared to 9.8, which is 10. Okay, so this is several orders of magnitude, 2 to 3 orders of magnitude, smaller than gravity. And that's why you don't feel like you're accelerating. Okay? It's a very small number compared to gravitational acceleration. Okay, any questions about this approach? Lots of questions about this approach. How about in the back there?
So the further you are away from the radius, the slower you're going, your acceleration?
Well, let's see. He said if we are further away, do you have a smaller centripetal acceleration? That is certainly true for a given v, right? If we don't change v and you just increase your r, you have a smaller centripetal acceleration. But if, for instance, we keep the period the same and we go out to a bigger r, then the acceleration, in fact, goes up because r is in the numerator here. And that's because you would have to be going a lot faster to get to that same period. Okay? Excellent question. Other questions? Yeah, the front here.
So, since we solved this for our planet, there's other planets would have higher accelerations. Would you notice that if you were to walk on them?
Yeah, absolutely. We have not visited any other planets that have higher accelerations than us, but we, of course, have visited something that has lower acceleration than this, which is the moon, right? And the moon not only has a different gravity, but it has a different spin and mass and radius and everything. And so the centripetal acceleration is also very different on the moon compared to other planets. Yeah, and what we see here is also the following. If r gets very, very, very small, then the acceleration for any given orbit can get really, really high. And one of the smallest, most compact, dense objects in the universe is, of course, a black hole. And things that orbit black holes can have incredibly high accelerations, incredibly high centripetal accelerations. Okay, other questions about this? Yeah?
So if our gravity is 9.8 meters per second, if we had a small enough r, would we, I don't know, essentially float? Would that acceleration combat the gravity?
Okay, excellent question. Let's rephrase the question and ask it again.